So there are a couple of different ways, right, in order to write specifications, right. So one is using this assert and assumes. The other way is through precondition and postcondition, right. So we have already seen this particular syntax for precondition and postcondition, right. So you use this curly braces, right. So use something like P, C and Q, okay, where C is the program that you want to verify, right. So this is in the imp language, right, and P is the post condition and Q is P is the precondition and Q is the post condition, right. So this P and Q themselves are formula, right. They are first order logic formula whose free variables are the program variables, right. So let us now define the verification problem in terms of pre and post conditions, right. So of course I can always write like something like assume P, right, and then C and then assert Q, right. So what I am saying is that this pre-post condition based specification methodology, right, it can be reduced into this assume assert based methodology, right, in the sense that for this program now you only have to check whether or not this assertion is ever violated, right. So is the error state reachable or not, okay. So both the specification techniques, right, are equally powerful, right. So you can write specifications in either way, okay. But let us directly define this PCQ precondition post condition based specification, right, because we will see later, right, where having this precondition post conditions explicitly in the program is useful, okay, instead of assumes and asserts, okay. So we express the verification problem in terms of preconditions and post conditions, right. So now we say that a program satisfies the specification, right, PCQ, right, if this particular condition holds, right. So what does this condition say? So it says that for all valuation of variables, right, sigma and sigma prime, if sigma is a model of P, right, which means sigma satisfies P, and on executing the program, right, so this particular statement means that you execute beginning from this sigma the program C and you keep on executing, right. So I am using this particular star notation here, right. So this is the transitive closure. So this is the transitive closure of the of this particular arrow, right, the transition, the operational semantics, right, of the imp language, right. So if by some sequence of transitions, right, if I reach the state sigma prime skip, okay, so sigma prime skip means that I have executed all the statements of C, right. So this skip will occur only if all the statements of C have been executed, right. So if I terminate, right, which means that if the execution of C halts, right, which can only happen after all the statements of C have executed, and if I reach the valuation sigma prime, then this sigma prime should satisfy Q, right. So this is an arrow, right, it's an implication here, right. So in other words, right, what it is saying is that if you consider any execution of the program starting in a program state which satisfies P, and if the program terminates, right, if it executes completely, then it should terminate in a state which satisfies the condition Q, right. So it should terminate in a program state which satisfies the condition Q. So if that is the case, then we say that the program satisfies the specification PCQ. Now again you should convince yourself, right, that this particular PCQ based specification, this is the same as assume P, C assert Q, right, which I had shown in the beginning, right. So if you have if you change the program by adding this assume P and assert Q at the end, right, and if you search for an error state now, right, if you ask, okay, is the error state reachable, then that is the same as saying that the program satisfies the specification PCQ, right, in the sense that the error state will not be reachable if and only if the program satisfies the specification PCQ according to this particular definition, okay. And similarly, if the program satisfies the specification according to this definition, then the error state will not be reachable, right, in the other program with assumes and asserts, okay. Okay. So one thing that you should note, right, is that even though in this definition, right, we are seemingly using this particular formula, right, this is not in FOL, right, this formula is not in first order logic, right. Why is it not in first order logic? because we have already seen, right, that things like this transitive closure, right, cannot be expressed in first order logic, right. So this we are just using for the sake of exposition, right. You cannot construct a FOL formula like this, right. You cannot pass an FOL formula like this to any SMT solver, right, because something like this transitive closure, right, cannot be expressed in FOL. Okay. So we have defined this particular definition and we have used FOL only for the sake of exposition here. Okay. So this PCQ is also called a Hoare triple, right, and so we say that this if the program satisfies the specification PCQ, right, then this Hoare triple PCQ is valid, right. So going forward, right, we are, instead of saying that the program satisfies the specification PCQ, we will say that this Hoare triple PCQ is valid, right. So this valid is not the same as validity in FOL or something, right. So this is just some terminology, right. So we'll say that this triple PCQ is valid if the program satisfies the specification, right, PCQ, which in turn has this particular meaning, right, given by this formula. Okay. So both the ways that we have considered of specifying the verification problem, right, which is one is through assert assumes, right, and the other is through Hoare triples. They are both they both deal with what we call partial correctness, right, because they only consider terminating executions. Okay. So imagine that you have a program which does not terminate, right, which does not halt, right, which means that you can keep on executing that program, right. Now such a program will always satisfy the two specifications that we have seen. Why is that the case? Right. So let's consider the first definition, right, which was about the error state. So we know that the error state is a halting state, right, because once you reach the error state, there are no more transitions, right, there is no more execution. So if your program never terminates, it means that it will never reach the error state, right, and that in turn means that the program will be correct, right, because we said the program is correct if the error state is not reachable, right. Similarly, in the definition, in the Hoare triple definition, right, where we used the Hoare triple PCQ, right, there also we only considered terminating executions, right. So we said that there should be some sigma and sigma prime, right, such that the sigma c should go to sigma prime comma skip, right. So once you reach this skip, this is a terminating state, right, because there are no more transitions, right, outside out of this sigma prime comma skip, right. So if your program does not terminate, that means that it will never reach this particular state, right, because if it reaches this state, then that means the program is terminating, right. So if you have a non-terminating execution, then that particular execution trivially satisfies the definition of the Hoare triple, right. So you can look back to this definition, right, this is an implication, right. So this is the antecedent and this is the consequent, right. So if you have sigma and sigma prime, right, such that the program never terminates, right, which means that there does not exist such a sigma prime at all, right, such that sigma c goes to sigma prime comma skip, then such a program, right, will trivially satisfy this particular definition, right, because the antecedent itself will be false, right. So there won't be a sigma prime such that sigma c goes to sigma prime comma skip, right, and that's why such a program will satisfy the specification, right. So the Hoare triple will be valid. So in general, I mean, this is not an issue, right, but sometimes you may also worry about termination, right. So in fact, in the example, right, for this Microsoft Zune example that we had seen earlier, there in fact our specification was that the program should terminate, right. So sometimes you do care about termination, right. So you do care whether or not the program will halt, right. So for that purpose, we can define a separate criteria, right, a separate verification problem which is called total correctness, right. So total correctness requires all program executions to be of finite length, right. So both the specification techniques that we have seen so far, they don't talk about total correctness, right, they only talk about partial correctness. So for total correctness, we will use a slightly different notation, right. So instead of using curly brackets, we use this square brackets, right. So we say that this program C satisfies the specification PCQ, where I am using square brackets instead of the curly brackets, right. If again every execution which begins in a state satisfying P should terminate in a state satisfying Q, right. So if you start the program in a state which satisfies the formula P, right, the valuation of the variable satisfies the formula P, then you are guaranteed that this program will terminate, right. So in a finite number of steps, and when it terminates, it will terminate in a state that satisfies in a state that satisfies the formula Q. Okay. So if that is the case, then we say that the program satisfies the specification PCQ with square brackets. Okay. So let us again try to formally write down, right, what this particular definition is saying, right. So just like we defined, we use this first order logic formula, right, well not exactly first order logic, right, but for the sake of exposition, right, we use an FOL formula to define the partial correctness problem. Similarly, let's try to also define the total correctness problem, right. So we want to say that whenever you start the execution in a state which satisfies the formula P, right, then the program should definitely terminate, which means that in a finite number of steps it should go to the program itself, right, should be converted into skip, and the state should satisfy the formula Q. Right. So this is what we want to express. Okay. So let's look at the definition of partial correctness again, right, that we had seen. So for all sigma and sigma prime, if sigma is a model of P and if sigma C goes to sigma prime comma skip, right. So after some arbitrary number of steps, if it goes to sigma prime comma skip, then sigma prime should be a model of Q. Right. So this was the definition of partial correctness, which only cares about executions which terminate, right. So if an execution doesn't terminate, right, then those executions will satisfy this formula, right, because sigma C will not go to any sigma prime comma skip at all, right. So now we want to say that if sigma is a model of P, then in a finite number of steps, right, you should definitely reach some state where the rest of the program to be executed is skip rather, and the valuation of the variable satisfy Q. Right. So all we need to do, right, seemingly is we need to take this particular clause, right, and then move it to the consequent, and instead of using star here, right, we will say that there are some finite number of steps, right, which can be taken, after which the program will definitely go to skip. So that's what I am doing here. So I am saying that for all sigma, such that sigma is a model of P, sigma satisfies P, right, there exists some n, right, and some sigma prime such that sigma C will definitely go in n steps, right. So I am using this notation, right, which is this this arrow, right, the transition arrow, and then n in the superscript, right, which means that I am taking n transitions, right. So in n transitions I will definitely go to a state where the valuation of the variables is sigma prime, the rest of the program to be executed is skip, which means that I have finished the execution, right, of C. So there are no more statements to be executed in C. So here the program has terminated, right, and by the valuation of the variables, which is sigma prime, it satisfies the formula Q. Okay. So but let's try to think about this carefully, right. Does this really say what we want to say, right? So is it the case that if this formula is true, then the specification, right, this PCQ specification is satisfied, right, which means that whenever you start the program C in a state which satisfies P, then the program will definitely terminate and in a state which satisfies Q. So perhaps a bit surprisingly, right, this particular formulation is not correct. Okay. And so why is it not correct, right? And this is not correct because of a peculiarity of the IMP programming language, right, which is non-determinism, right. So we know that the language is non-deterministic, right, which means that there could be some executions which terminate, but there could also be some executions which don't terminate, right. So if you are in a state, right, let's say sigma C, right, where sigma is a model of P, then there could be one execution of the program which terminates, but because the language is non-deterministic, there could be another execution, right. So I could reach sigma prime comma skip here, but there could be another execution, right, which doesn't terminate at all, right. So this particular formulation, right, it allows something like this to happen, right, because it only says that there exists some execution, right? There exists some n in sigma prime such that sigma C goes to sigma prime comma skip, but it doesn't say that, it doesn't prohibit, right, executions which don't terminate. So it just says there is some execution which terminates, but it doesn't prohibit all non-terminating executions, right. So this is what we want to do, right. So we want to prohibit all non-terminating executions. So we want to say that there should not exist any execution, right? So even if there is non-determinism, it should not allow executions like this, right, which don't terminate. So to summarize, right, this particular formulation, right, this is incorrect, and this is incorrect because it says that for every state satisfying P, there is some execution which starts from that state, right, and which terminates in a state satisfying Q, but it doesn't say that all executions which start from the state in P terminate, right. So imp is non-deterministic, because of which there could be some executions, right, which start from a state in P and they also terminate, but they also don't terminate, right. So separate executions, right, where one execution terminates and one execution does not terminate. So let us see how we can more precisely state this notion of total correctness. Okay. So this is the more precise definition, right, of total correctness. So let's say what it is saying, right. So it's essentially giving a bound on the number of steps taken by any execution, right, of the program, right. So it's saying that for all sigma there exists this n. So this n is, you can think of as the bound, right. It's the maximum number of steps taken by the program in any execution, right. So we are saying that there exists such an n such that if sigma is a model of P, so if sigma satisfies P, right, then it is not the case, right, that beginning from sigma, if I execute C, in m steps I go to some state sigma prime comma C prime where m is greater than n. So I cannot execute the program C for more than n steps, right. So there does not exist any m in sigma prime such that m is greater than n and I can execute sigma C for more than n steps, right, for m steps. Okay. So this means that every execution of the program, right, it cannot take more than n steps, right, it has to terminate within n steps. And furthermore, I am also separately saying, right, that if it does, when it terminates, right, so if in some number of steps, right, sigma C goes to sigma prime comma skip, then that sigma prime should satisfy Q, right. So in addition to saying that every execution of the program terminates, right, because every execution of the program, its length should be less than this n, I also need to say that every execution terminates in a state which satisfies the specification Q, right, which satisfies the formula Q. Okay. So this is the more precise, right, this is the precise definition of total correctness, which is given by the specification, this PCQ. Okay. So in this course, right, we are mostly not going to deal with total correctness, right, we will only worry about partial correctness, right? But as we have seen, right, in so in the example of Microsoft Xeon, right, that you can convert total correctness to partial correctness, right, in the sense that you can always find appropriate assertions, right, to make sure that the program terminates. Right. So that's why we won't deal with total correctness, right, because it can be reduced to partial correctness, right, by adding appropriate assertions. Okay. So here is an example which demonstrates what we have been discussing so far, right. So if you look at this program, okay, the first thing that you should notice is that this is talking about total correctness because I am using the square brackets here, right, instead of partial brackets. So this is the precondition, this is the post condition, right. So this is P, Q, and this whole program is C, right. So I am saying the precondition is true, the post condition is I is not equal to phi. Okay. And let's see what the program does, right. So this particular program is non-deterministic. So it starts with a havoc statement, which means that after executing havoc, I can have any value. And then it says that if I is equal to phi, right, then I have this particular loop, right. So what does this loop do? This loop is a non-terminating loop, right. So as you can see, it simply keeps on incrementing the value of I while I is greater than 0, right. So if I is equal to phi, then in every iteration you will simply increment I and then this loop will never terminate, right, because this condition will always be satisfied. On the other hand, if I is not equal to phi, then you're just skipping, right. So which means that the program will terminate. Okay. So take a moment, right, and think whether or not does this program satisfy our total correctness definition. Okay. In the sense that is it true that if you start the program in any state, so because P is true here, so if you start the program in any state, is it always the case that the program will terminate? And clearly that is not the scenario, right, because if you consider an execution, right, where after this havoc statement I is assigned the value phi, then in that particular execution this program will not terminate, right. But in any other execution where the Havoc statement assigns a value to I which is not equal to 5, this program will definitely terminate. And if it terminates, right, then it will actually be in a state where I is not equal to 5, right. So therefore, this program does not satisfy the total correctness criteria, right, it does not satisfy the specification. And if you had looked at our previous definition, right, so this was our previous definition of total correctness, right, which was incorrect, right. So it said that there exists for all states sigma, so that sigma is a model of P, there exists an execution, right, which terminates. And in fact, according to this definition, right, this program does satisfy this particular formula, right, because for every state, right, for every initial state, there does exist an execution, right, where in that execution the Havoc statement gives a value to I which is not equal to 5, right, and in that particular execution the program will definitely terminate, but there are clearly non-terminating executions as well, right. So this particular program does not satisfy this formula, right, because you cannot give a bound on the maximum number of steps that are taken by this program in any execution, right, because there are non-terminating executions. Right. So if you were to, for example, replace this total correctness with partial correctness, right, so if you had something like this, instead of using square brackets, let's say if I used curly brackets, right, and then the same program. So does this program now satisfy the partial correctness criteria? And indeed it does satisfy the partial correctness criteria, right, because partial correctness only says that when the program terminates, it should terminate in a state which satisfies the post condition, right. So even though this program has non-terminating executions, but when it does terminate, right, it will always terminate in a state where you will go in this else branch, which means that I will not be equal to 5, right. So this program satisfies the partial correctness specification, but it does not satisfy the total correctness specification. Okay, so now let's look at some very simple examples, right, of this Hoare triples, right. So Hoare triples are this triples P, C, Q, right, where P is the precondition and Q is the post condition. Okay, so let's see these 4 Hoare triples, right. So what can we say about this Hoare triples? So let's go through them one by one. So the first Hoare triple is saying that T, which is top, right, which is true. So true CQ, right, what that means is that the precondition is true, right, the program is C and the post condition is Q, right. So do there exist programs C and post conditions Q such that this particular Hoare triple is valid, right. So what this Hoare triple is saying is that no matter what the initial state of the program is, the initial valuation of the variables is, right, so there is no precondition, the precondition is true. If you execute the program C, then you will always end up in a state which satisfies Q, right. So for example, right, let's consider something like this, right. Suppose I had something like x equal to 1 and then x equal to 1. Right? So this Hoare triple is valid because no matter what the initial program state is, right, which means no matter what the initial value of x is, after I execute this assignment statement x equal to 1, it is definitely the case that the valuation of the variable, right, the valuation of x at that point will satisfy the post condition, right, which is x equal to 1. Right. So this is an example of a Hoare triple of this form, right, which is true CQ, right, where the precondition is true, right, but there are many other examples, right. So as a homework, right, you can try to come up with other examples of C and Q, right, which will satisfy a Hoare triple of this form. Okay. Let's look at the second one, right. So this is saying false CQ, right. So here the precondition is false, which means that no state satisfies the precondition. So here, right, if you again look at the definition, right, of this Hoare triple, right. So let me write down this definition again, right. So for all sigma prime, if sigma is a model of P and sigma C goes to sigma prime comma skip, then sigma prime is a model of Q. Right. So if my precondition is false, right. So if my precondition is false, that means that there is no sigma, right, which will satisfy the precondition, right. So in fact, since this is over for all sigma, right, and every sigma will not satisfy the precondition, which means it will not satisfy the antecedent, right, which means that this formula will actually be true, right, because for all sigma prime, in fact, this particular formula will be true because the antecedent will be false, right, because sigma is not a model of P, right. So therefore, for any C and any Q, this Hoare triple is always valid. So no matter what C is and no matter what Q is, this Hoare triple is always valid because the precondition itself is false, right. So essentially this is simply saying that if you start in a state where the valuation of the program variable satisfies false, then if you execute C, you will always end up in a state which satisfies Q, right. But there is no state where the valuation of the variable satisfies false, right. That is why this particular Hoare triple is trivially true, right. So, this is what we call as trivially true or trivially valid, right. So, for all C and all Q, this Hoare triple is valid. Similarly, let us look at this one, right. So, here this is another example of a Hoare triple which is trivially valid. For any P and any C, this Hoare triple is always valid, and the reason is that the consequent, right. So, since Q is equal to true, since the post condition is true, no matter what sigma prime I take, it will always satisfy the consequent of this formula, right. So, this is an implication, its consequent will always be true for all sigma and sigma prime, right, because all sigma primes are models of true, and therefore, this is also another example of a trivially valid Hoare triple, right. So, no matter what P and C I take, this Hoare triple is always valid. Finally, let us look at this one, right. So, this is something interesting. So, it is true C false, right, which means that the precondition is true, the post condition is false, and the program is C. Okay. So, does there exist a program C for which this Hoare triple is valid? So, when will this Hoare triple be valid, right? So, it will be valid if for all sigma sigma prime, right. Sigma is a model of P, but P is true, so all sigmas are models of true. If sigma C goes to sigma prime comma skip, then sigma prime should be a model of Q. So, if it is the case, right, that the program terminates in a state which in a state sigma prime, then sigma prime should be a model of Q, but Q here is false, right. So, the consequent is always false. That means that if the antecedent is ever true, right, then this particular formula will not be valid, right. So, if you have a program C where the antecedent is always false, which means that there is no sigma prime for which sigma C goes to sigma prime comma skip, which essentially means that for non-terminating programs, right. So, if you have a non-terminating C, then this particular Hoare triple will always be valid, right. So, this Hoare triple is valid only for those programs which are non-terminating in any state, right. So, beginning from any state, they should be non-terminating. And again, right, let's think about this intuitively, right. So, intuitively this Hoare triple is saying that if you start the program C in a state which satisfies true, then if you terminate, you should end in a state which satisfies false, right. But there is no state which satisfies false, which means that if you do not terminate at all, right, then you will trivially satisfy this formula, right. But if you terminate, then you are in trouble, right, because then you have to terminate in a state which satisfies false, but there is no such state, right. So, if you have a non-terminating C, then this particular Hoare triple will be valid. Okay. Let us look at a couple more examples which demonstrate the difference between partial and total correctness, right. So, we have already kind of seen one example earlier, right. Let us look at another example, right. So, let us consider this program. Okay. So, again this is a Hoare triple, right. So, this is the precondition, this is the post condition. Notice that I am using curly brackets, which means that we are talking about partial correctness, right. So, what is this particular Hoare triple saying? So, it is saying that if you start in a state where the value of x is 0 and you execute this particular program, which is just a while loop, if you terminate, you should terminate in a state which satisfies the post condition, right, which is x equal to 1. So, in fact, this Hoare triple is actually valid, right, because if you start in a state where x is equal to 0, then this while loop will never terminate, right, because it just keeps on incrementing the value of x in every iteration, right. So, x will always be greater than or equal to 0, and therefore, there are no terminating executions, right. So, all executions are non-terminating beginning from a state where x equal to 0, right, and that is why you do not need to check the post condition at all. That is, the post condition needs to be checked only if the program terminates, right. So, if the program terminates in some state, then only you should check the post condition. Since in this particular case, the program never terminates, right, beginning from a state where x is equal to 0, that is why this Hoare triple is valid, right. So, this Hoare triple is valid, but this is talking about partial correctness. So, if you were to replace this curly brackets with square brackets, right. So, that is all I am doing here, right. So, I have replaced this curly brackets with square brackets. Now, we are talking about total correctness, right. So, for total correctness you are asking, beginning from a state where x is equal to 0, every execution of this program should terminate, and it should terminate in a state where x is equal to 1. So, in fact, this Hoare triple is clearly not valid, right, because if you start in a state where x is equal to 0, then all executions are in fact non-terminating, right. So, you will never terminate.